Hey everybody, it's Mrs. Cassill again. So now we're going to work on the rolling yo-yo. Okay? Imagine you were stuck on a desert island and for some reason a maniacal genius had trapped you there and your quandary was if you can show what the moment of inertia for a coconut you're rolling down the beach is, then you get off the island. Well, you might take this approach several different ways. How do you figure out the moment of inertia of a coconut? Well, you could roll it, you could throw it, you could drop it. There's lots of different ways to make it move in order to observe that motion and determine why that motion is occurring. That's essentially what you're doing in this problem. You let a yo-yo fall on the string, and based on that acceleration data, you can determine the moment of inertia. A second way to do that is to let the yo-yo as a complete object roll and see how is it moving rolling wise. This approach, if you think about the first part, this approach is all about energy. And if you remember when we learned about energy the first time, in a lot of ways, it's just a different flavor of doing forces. That's why they end up connecting when we get to the work kinetic energy theorem, right? So energy is a very elegant and simple way of solving problems because it's a scalar quantity, and what you started with is what you end with. It's conserved, unlike forces that are applied all over the place and you've got to account for every single one. So let's think about what's happening to our yo-yo here. You've got a ramp, okay? At the top of the ramp, your yo-yo is joyfully sitting there, and in slow motion, the moment I let go, it is not moving. That first moment right there, the velocity of the yo-yo is 0. So you know a couple of things. At the top of this ramp, this yo-yo only has potential energy due to gravity. It has no other energy. The ramp is doing some work there and it's changing the acceleration so it's not just in free fall directly down. But we don't actually care about what the ramp is doing. I'm going to ignore it completely because that's what energy is awesome for. What I start with has to be equal to what I end with. So who cares what happened in the middle? So at the end, I gotta get another color marker here. So at the end of the ramp, here's our yo-yo, and it's rolling along, and it should be traveling at a constant velocity. In fact, that's the only part of the data that you need to analyze in order to determine numbers that you can use for this part of the problem. So, and I can tell you the data is good. It's moving at a constant velocity. It worked out pretty good. So you've got your yo-yo rolling along. So let's think about what kind of energy it has. Does it have a velocity that way? Yes, it does. So it has kinetic energy. And remember, we use this word translational. So it's got this kinetic energy because it's moving from left to right. So that's equal to 1/2 mv squared. The good old other thing that's happening to your yo-yo, so it's not just that it's moving in a linear fashion, it's also rotating, right? As it's going around here, that's what's making it move to the left and right, from the left to the right. It's rotating. So we also have kinetic energy that's rotational, and that's equal to 1/2 times the moment of inertia times omega squared. And remember, if you don't remember, omega is our angular velocity. That's how many radians that yo-yo is rotating through any given amount of time. Now, did anybody have a rotational sensor on the video? Not me. So I know a few more things here. I know that a linear velocity is equal to the radius of something spinning or rotating times its so I can solve this for angular velocity, linear velocity divided by radius. And I can plug that in omega. So let's look at what we've got here in this problem. It comes together so nicely, right? I've got that my conservation of energy tells me I've got gravitational potential energy started with the beginning. And then I have rotational kinetic energy plus translational kinetic energy. So I'm going to look at my equations for each of these. My equation for Gravitational potential energy is the mass of an object times the acceleration of gravity times the height that the object travels through. Those are all numbers that I know, right? That's my 1/2 times my moment of inertia times that angular velocity squared, which I'm going to substitute for in a second, plus 1/2 times the mass of my object times the velocity. Don't get carried away and cancel out mass yet, because we actually don't know how much mass is factored into this moment of inertia right here. We don't want to cancel out mass because there isn't a mass. We want that letter I. That's the thing we're trying to solve for. So at this point, we now have a big algebra problem. The thing that you're going to figure out, right, when you think about your known and your unknown values, you actually know everything in this problem. Oh, and you'll hear my cat complaining a whole bunch that I'm not playing with him right now. Right? You know the mass of your object, 0.000, oh, 14 kilograms. Yeah, that's right. Yeah, okay, sorry. Sometimes when you're not sure, it's good to stop and check your work. We know the acceleration of gravity, 9.8 meters per second squared, because energy is a scalar. I don't have to care about positive or negatives here, especially because my zero line, I'm basically defining this as my zero line. So, height, I believe, was 4 inches. I think that's what I said in the problem. So you'll want to turn that into meters. Let Google do that for you. Memorize a formula unless you really, really want to. I know that my omega is going to be equal to velocity divided by the radius. And in this case, that radius is the outer radius, right? That's the outside of the wheel. So it's really important that you use your number for the outside radius. So which was 0.025 meters. And your velocity is your only value left, right? So this velocity right here is going to be the thing that you figure out from your data. So you're going to need to look at the distance and time data to determine what that velocity is. And now you have every number you need to solve for your moment of inertia. All right. Tip two, I recorded those videos in slow motion, but if you pull them up on YouTube, you can slow the videos again, right? You can put it down to 1/4. And if you quick tap on your video, it literally goes frame by frame. So you can play pause, and get the yo-yo to move exactly where you want it in order to observe what the distance is. All right, everybody. I hope this helps, and good luck. You're doing a great job.